So, as promised, we've got the other nucleophiles. When we're looking at adding our strong acids, there are ways that we could add a strong acid, a non-nucleophilic strong acid. So our non-nucleophilics, let's go ahead and write that up. Our non-nucleophilic strong acids, the big classic one is H2SO4. Sometimes you could see H3PO4 also included. Why the difference? H3PO4 is a slightly or significantly weaker acid, so it tends to not burn the crap out of things, whereas H2SO4 will just burn the crap out of it and overreact it. So H3PO4 will still supply those hydrogens, but at the same time not so active that it just destroys stuff. Okay, so why is this important? So when we're looking at this, if we use a non-nucleophilic strong acid, we now have the potential to add as an additional feature, add a secondary nucleophile, which is kind of neat. So instead of just adding halogens, we could add other nucleophilic atoms. Well, considering that this is OChem and we decided to drastically simplify our periodic table, that really only leaves us with two other possibilities, O and N. Because we're already adding a strong acid, we're going to have to protonate these. So we could add them as H2O and NH3. Hopefully, I just set off alarm bells in your little head on where this could go, but we'll see this in a second. Okay, so cool. We now have those as potential sources because they have electrons. Okay, so all those notes are about to disappear. Yeah, both of those notes are about to disappear. So couldn't we, following the same pattern that we have done up here, okay, with our halogen, go through and run a similar system with our nitrogen and oxygen nucleophiles? So ta-da! Aren't those potential reactions that we could run? Yes and no, quite literally. Yes, this is a possible reaction, and no, this one is not. Okay, so when we're looking at our oxygen nucleophile, the oxygen atom is a nice balance of electronegativity that allows it to still share electrons in this particular reaction. Okay, so we can get the oxygen to act as a nucleophile. That's fantastic. The nitrogen, on the other hand, because it's a little bit less in electronegativity, doesn't hold on to its electrons quite as well. Okay, quite as well, which means it gives them up pretty swiftly. And what do we mean by gives them up pretty swiftly? It gives them up to the most accessible and ready chemistry. The most accessible and ready chemistry is acid-base chemistry. And so what happens with the nitrogen nucleophile is that NH3 very swiftly goes to NH4 plus in that strong acid environment. The instant it does that, we've now killed the nucleophile. Okay? So if there's no nucleophile, then we can't get the second step of this reaction, the nucleophilic addition, and instead what we end up with would be a carbocation that can never ultimately end up getting stabilized, and this is where we get burning of our reagent. All sorts of other secondary reactions happen, and we don't get a high yield of anything in particular. Okay, we just get tar. We would see this with the H2SO4 reaction because we use these reagents with our H2SO4 in an elimination as well. And yeah, you end up with a tar. Okay, so that means when we're looking or thinking about our reagents under the acid conditions, we're looking at our halogenations and we're looking at oxygen. Okay, those are the two valid nucleophiles to go through and sequentially use. Some names that could get thrown out there with that. The halogen ones that we've walked to are sometimes referred to as hydrohalogenation because we're adding a hydrogen and a halogen. Way to be creative. When we look at the other one, we'll refer to it as a hydration because we're now adding hydrogen and OH. So we're adding water across a pi bond. This is where people tend to freak out and be like, well, all I added was the OH. Remember, you also added that hydrogen from our water too. Okay, so it's a hydration reaction. In the eliminations, where we reverse that process, we could refer to it as a dehydration or a dehydrohalogenation. Okay, and that came from our elimination nomenclature. Because we're not eliminating, we're adding, we can just drop the D and everything becomes happy. Okay. We're about to see a whole bunch of stuff pop up. Don't worry about that stuff popping up because I'm going to skip over it. And what we can see is the mechanism for our oxygen nucleophile mechanism. And so we've got our reaction. Note that we're not seeing H2SO4 being our active acid. We're seeing H3O+. Why H3O+? Well, that's that leveling effect way back in chapter 6 or 7. H2O or H3O+ is a weaker acid than sulfuric acid, so that has to form first. We protonate. We now have our water that is present. The water can now attack our carbocation. We can then do the deprotonation of our hydrogen. Okay, so if we, and this is going to become relevant here in a second, we have our acidic hydrogen, and then we have a deprotonation of that hydrogen to stabilize our oxycation. Okay, because we'd be forming a positive charge on that oxygen. Okay, you'll note that we didn't have to do that step with the halogens because the halogens didn't have another hydrogen on there. They only could form one bond. Okay, so we have to stabilize that oxycation, and then we'd have our final product. Okay, so there's really two hydrogen exchanges happening. So that extra hydrogen exchange is an important one for the oxygen nucleophile. Okay, which then gets us to the questions down below. Does the oxygen have to come from water? Okay, are there other places that oxygen could come from? Well, ethers have an oxygen. Could an ether satisfy the requirements of the mechanism? Okay, well, theoretically, we've got the acidic hydrogen, so we don't have to stress about that happening on this structure. So the acidic hydrogen could just come from our strong acid, okay, our H2SO4. So that one's not critical. The one that is critical is we have to stabilize the oxycation once it forms. If those were now two methyl groups, a CH3 and a CH3, do we have a way to stabilize the oxycation? Well, sort of. The way is that we take the electrons back from the carbon that we just formed that bond with. Okay? That would mean undoing the reaction we just did. Okay? So the oxygen from an ether doesn't allow the reaction to happen. Okay? So we might say, well, then no, we can't do this. It has to be water. Okay? Well, are there other oxygen-containing functional groups? Like an alcohol. Why has the alcohol now become different? That alcohol still has that secondary hydrogen, okay, or that second hydrogen that can stabilize the oxycation, and that can be removed during the mechanism to ensure that we end with a proper product. Okay, why does that become different? If we start with an alcohol, what functional group will we end the entire reaction with? So if we track through all the pieces shown above, hopefully what you would see is instead of that being a hydrogen, our purple, instead of that being a hydrogen, that would come in as a CH3. And if we start with an alcohol, we'll end with an ether. Okay, so we have a way to synthesize ethers in this fashion. Okay, so the requirements of that oxygen source is that it has to have at least one hydrogen so that it can stabilize the oxycation when it forms through that mechanism. The initial red acidic hydrogen can just come straight from H2SO4, so we don't need to stress about that one. But I do need that blue one to stabilize the oxycation. And why does this become potentially an issue? Well, what students end up seeing is that this now means that there's two different reactions. We've got water and we have alcohols. They're both doing the exact same thing. Okay? There is one reagent. That one reagent is the oxygen nucleophile. What I'm addressing is what other secondary chemistries have to be present to allow that oxygen nucleophile to react in electrophilic addition. Okay? So try and step away from that memorization of it's a new reagent to now focusing on it's the same chemistry, it's just a slight different spin on it. To give you an idea on that, what I'm going to do is pause the video and jump to our reaction summary, because we've now covered a sizable amount of reactions on that. So I apologize, I may have just recorded me going back through the slides and then paused when I got to the slide. So here we go. Here's our summary. We're looking at HX, where X was a halide. We then just threw in just now where X, if we want to, would be water, or really just oxygen, where that oxygen was connected to two hydrogens. And we've also addressed now that we have X equaling an oxygen, where the things that were connected to our oxygen were hydrogen and carbon. So we now have three different reactions. All three of these are following the same patterns. So if you can understand the pattern of the chemistry, you don't have to memorize three distinct things. You've got it nailed down in one. Okay, so that's the intent behind that, and why I want you to be looking at the mechanism behind these processes, not just memorizing reagents. Okay, so with that, we'll go ahead and end this video, a nice little short one.